towards the Peak District hills. So it's really quite pretty. And there is the atmosphere of Manchester. So we have now minimal pollution. I started in about 1986, and we could have measurable acid rain. And now, 20, 30 years later, the pollution, the acid rain pollution particularly, is minimal, or the vehicle pollution is a lot higher. So what do you expect from this talk of mine? Like many of these, I'm going to tell you how I got here. So have a quick review of my career. And more importantly, who has helped me get to where I am at the moment. I'm going to show you a few things I've done over the last 35 years. Some of you may well have seen these before, so I apologize. And again, I'm completely humbled by having the award, and many thanks to all those who supported me in it. So way back in 1983, when it was another economic slump and there weren't very many jobs around, George Thompson hired me to undertake research in atmospheric corrosion at the Corrosion Protection Centre at UMIST. This is the original screen plaque of UMIST, and this is the new modern one. A colleague resigned, a colleague of George's resigned, Peter Elliott. He resigned in 1985, creating a vacancy, and I was encouraged to apply by Robin Proctor. Graham Wood supported my early research, and he's the other one who won the European Corrosion Medal in Manchester. And this is why it's amazing that I've managed to win it, because Graham had such a worldwide reputation in the area. My colleagues in the UMIST days, David Scantlebury, Dave Moore, Steve Turgus, John Dawson, Bob Cottis, Howard Stott, Roger Newman, Margaret Stack, and others advised and inspired me over those years. In 2004, Victoria University of Manchester and UMIST merged to create the University of Manchester, which is where I am now. But before they merged, we took this picture here. This is the main key staff. There's Graham Wood there. There's David Scantlebury, that's George Thompson. But many of these people have now retired. Roger Newman is now in Toronto in America. So in the UMIST days, these are the people who work with me, visiting fellows, postdocs, PhD, MPhil students. I'm not going to go through them all. And in 2004 to present, these are the people who work with me, again, lots of them. And we mustn't forget the undergraduate and master project students, of which I've run through about 90. They have been very supportive and long-suffering of my whims and requirements throughout these years. So I'm also very grateful to them for being really good. I don't think I've had a single bad one amongst them. They've all been fantastic. And they also come from 6 continents. I don't have any penguins yet, but obviously I think I've got the same number of people working with me over the years as this conference has in attendance, which is fantastic. And these are some of the sponsors that I've had working with me. Currently at the moment, I've worked with International Paint, which is a part of AkzoNobel for best part of 35 years. AkzoNobel is the new owner. Courtaulds was the old owner. And many of these other, I have worked in the nuclear industry, the oil and gas industry, etc. So many, many research sponsors. So how do we go about doing experiments? And I love this quote. It was originally a week in the library saves a month in the lab. Of course, libraries aren't really used anymore, so it really means a week reading and thinking saves a month fiddling around doing nothing in the lab. And one of my researchers was very much criticized for apparently doing very little by his colleagues. But their experiments always work first time, which is very annoying to his colleagues as well. And that's because he spent all the time thinking about what to do, designing the experiment correctly, testing his hypothesis using a thought experiment, and then running the experiment properly first time. And that's really a good idea to go through life. I can't guarantee that all my work has been like that, but hopefully some of it, or some of the most important parts of it, have been. So what do I work in? Well, I'm running through a program of atmospheric corrosion. I was hired to do atmospheric corrosion. And this rather lovely movie shows atmospheric corrosion on steel over 2 months exposure. And as you can see, we can see apparently filiforms running across the surface. This is not a painted piece of steel. This is just bare steel being time-lapse photographed. We can see these little filiforms running all over. We can see little deposits of salt here. And after 2 months, significant parts of the steel are still bare. So these are obviously where the anodes were. And maybe these are cathodes, or maybe they're passive. We just don't know. I love that so much, we're going to run it again. So if you're not seeing corrosion in action, this is corrosion in action. And atmospheric corrosion is a fascinating subject because it is so potentially difficult. So the corrosion rate of steel in the atmosphere is quite similar to the corrosion rate of steel immersed in seawater. And why would that be? Seawater should be more aggressive than the atmosphere. So there are many interesting questions. There we go. So we needed to prepare naturally rusted iron samples for an experiment I'll show you shortly. And we put 16 wires embedded into an epoxy mounting resin, put them on the roof of our lab in Manchester, roof of the building I showed you earlier, and we expected them to corrode within a week. However, after a week, only 4 had corroded and 12 were uncorroded. And even after 3 months, 2 of them were like that, completely uncorroded. The rest of them were like this, all rusty. And that's quite interesting as well. Why would that happen? This implies that there is something controlling or stopping that corrosion to occur, probably because the material is passive. So based on this observation, one of the hypotheses I ran with first is that iron or steel retains some kind of passivity during the corrosion process in the atmosphere of wetting and drying. So if we have evaporation condensation cycles, we can see after a very short period of time, 4 to 5 wet-dry cycles, the steel reaches a passive state. If we do electrochemical experiments in really dilute electrolytes, this is 10 to the minus 1 millimolar sodium sulfate, then the passivity becomes easier as the electrolyte thickness decreases from the bulk to the 100 microns. And a question that came up with the review of the paper was, this is all IR drop in the electrolyte. So we check that by increasing the electrolyte concentration by adding 2 drops of 0.1 molar concentrated sodium sulfate. Passivity stays the same, IR drops reduced, and we retain passivity. However, if we add chloride, it immediately starts pitting and we get a big increase in current. So the material is indeed passive under these conditions. Going on from atmospheric corrosion of steel, Evans' electrochemical theory was based on the redox cycling of iron oxides during atmospheric corrosion. And again, a hypothesis arising from the Evans model is that the reduction of iron oxides formed during corrosion is kinetically faster than the oxygen reduction reaction. And again, we check that. And you can see now why I wanted rusty electrodes, small electrodes on the surface of the sample. Here is our shiny uncorroded system. This is freshly polished. So this is the oxygen reduction reaction. It's about 50 microamps per square centimeter, which is about right. For a small electrode, you have radial diffusion, which increases the nominal rate. However, on a rusty surface, our corrosion rate, or our cathodic current at the same potential, is much, much higher. And the only reason that can possibly be is that the reduction of iron oxide is kinetically a lot faster than the reduction of oxygen. So Evans was not able to do this experiment in his day, in the 1960s, but he was right. He had great prescience. So moving on a little bit further, now on to still passive materials. This research came out of the nuclear industry, where they're interested in retaining nuclear waste in stainless steel containers for forever, essentially. And they were running with this comment, which is very, very common. General experience suggests that SCC of stainless does not occur below 50 degrees, except in particularly acidic conditions. And this is still being stated by the SSNA in 2020 on their website. And that's a wonderful thing if it was true. Unfortunately, it's not true. It does happen. This is 50 degrees, less than 50 degrees, and we can see underneath insulation, we do get stress corrosion cracking, but we get stress corrosion cracking even in the absence of insulation in a service environment where the temperature is well below this 50-degree limit. The question is why that is. And I can't do a talk on atmospheric corrosion without mentioning Vernon. And this is one of his classic experiments where he takes samples of materials, steel in this particular case, which have been contaminated with particular materials, silicon particles from the atmosphere, common particles at that time derived from coal burning. So we have charcoal, ammonium sulfate, etc. And he's raising the humidity until a corrosion kicks in. So this is the critical relative humidity for corrosion, round about 75 or so %. So in the absence of SO2 contamination, we get quite low corrosion rates. In the presence of ammonium sulfate, we get a significant increase in corrosion rate. With no particles, we get this corrosion rate. Interestingly, with silica particles, inert particles, we still get an increase in corrosion rate, and that's due to the crevice corrosion or differential aeration effect underneath its particles. So you then have the hypothesis that since ammonium sulfate isn't present in the atmosphere anymore, perhaps it's sea salt particles that give rise to this ambient temperature stress corrosion cracking of austenitic stainless steel, because it's well known that particulate deposits can influence atmospheric corrosion. So we did this small tensile experiment using a proving ring with this wishbone sample, bow tie sample. And at 40 degrees centigrade, although we've run these experiments down to about 20 degrees centigrade, and the initiation time for cracking just takes longer and longer. So at 30% humidity, most of the sea salt solutes have precipitated. You're just left with about 6 molar magnesium chloride. So if anyone does experiments at boiling magnesium chloride, it's about the same molarity. So you can see these samples have cracked here. And what we wanted to do is see if we can image these cracks over time to get a crack growth rate, and then use fracture mechanics analysis of the sample to understand whether what the K1SCC fracture mechanics threshold for cracking was. I'll just run this animation. You can see the crack. As the crack develops, this scale here, color-coded scale, shows the lateral movement in the sample by digital image correlation, and we can see the crack is actually bifurcated at that point there. There are 2 cracks here, so there's a pit, crack has grown that way, but it's mainly grown that way. So the pits initiate under salt droplets, and stress corrosion cracking initiates in this pit after some kind of initiation time, a delay time, in this case round about 1650 hours, that's about 10 weeks. And by measuring the linear displacements using this digital image correlation, we can get a crack opening displacement, which we can turn that into a crack tip stress intensity factor. So in this particular analysis, we can calculate the load from the unloading curve on the proving ring. And the crack initiates, as said, after about 10 weeks, with a crack growth rate of about 8 times 10 to the minus 10 meters per second. And the crack growth rate decreases as the load relaxes, and the crack arrests at 650 newtons. This is not a constant load experiment because of the proving ring, nature of the proving ring. So we turn that into a fracture mechanic approach. We find that the crack, in fact, initiates at a stress intensity of 10 megapascal root meters. That actually is the K1SCC for macroscopic compact tension samples. So it's exactly analogous to a macroscopic example. So stress intensity rises as the crack grows until edge interaction causes the crack to arrest. Essentially, that's a fracture mechanics interpretation of the crack arrest event. So the fracture mechanics stress intensity rises, and as it hits the edge, it falls back to the level. So how do we control atmospheric corrosion? This got me into protective coatings. So we can remove water, we can dehumidify the system, we can remove the oxidant, we could use contact corrosion inhibitors in wrapping and packaging, we can use vapor phase corrosion inhibitors. But all those are very well known mechanisms of how they do it. However, we could use protective organic coatings. We have a polymer binder in such cases, we have solid leachable active species such as chromate. We have pigments in the nano to micro size. So we can paint, we can call it a functional polymer matrix nanocomposite material. I quite like to use that description of a paint because it sounds much more scientifically exciting than just paint, because that's exactly what a paint is. It's a complex formulated product. So it's much more fun to figure out how paint works than to remove oxygen from packaging. So the first thing we looked at was chromate in paint, as many people have. Chromate is a really effective corrosion inhibitor for organic coatings, and replacements for chromate are mostly inferior. And one hypothesis was that chromate passivates steel underneath organic coatings, and other effective inhibitors therefore must do the same. It must be said, of course, that chromate at these low concentrations doesn't really passivate things. If you do an electrochemical experiment, you find that chromate acts as a cathodic dominant inhibitor rather than an anodic inhibitor, because the precipitation of chromium-3 oxide, reduction of chromium-6 to chromium-3 at the cathode. However, we used a scanning Kelvin probe to analyze this. This is a polyester coating, which is loaded either with strontium chromate or with an alternative phosphate-based inhibitor, or is blank. We drilled, or we laser ablated a defect in the coating at this location here, and we ran the Kelvin probe over it after exposure. And we found that in the chromate case, well, in all cases, in fact, the potential at the defect was elevated, which if you go back to the cyclic potential experiments I showed you in a few slides back, makes sense, because if effectively the exposed surface becomes passivated in the atmosphere by atmospheric oxygen. And what we found was that the chromate, in essence, didn't do anything to the exposed potential, but it raised the potential of the substrate underneath the paint. So if you imagine that the potential difference between the defect potential and the substrate potential drives the coating despondent process, then that's how chromate works. In the absence of chromate, we have this big potential here, from here to here in the blue line. Presence of chromate is much, much less. The driving potential for coating despondent is much less. So chromate is present in this case at about 700 ppm in the leach state under saturated solubility. We use an alternative inhibitor, which was found to be relatively effective, not as good as chromate, but relatively effective. And that's present at about 20 ppm in the saturated state. And what that did, instead of altering the substrate potential, raising it, it reduced the defect potential. Not quite as well. You can still see there's a bigger potential difference between the defect and the substrate, but that potential difference has dropped. So chromate is effective because it increases the substrate potential, so it's close to the defect potential, which is in support of that hypothesis. Phosphate is also effective, but in the opposite way. It reduces the defect potential, so it's closer to substrate potential, which goes against the hypothesis. So that hypothesis is sometimes right and sometimes wrong, which means it's not a universal idea. So that was one of the first things we did with paint. We then moved on to coil-coated steel. The big thing about coil-coated steel is the cut edge. It's a very well-engineered system. Steel core, we have a zinc or zinc alloy coating, chemical conversion layer, primers containing the inhibitor, and on the top face, a visually attractive material with UV protection and an appearance. So exposed steel and zinc alloy at the cut edge comprise our galvanic cell. And essentially, this is the big driver for corrosion of these systems. Unless the surface is damaged in some way, the cut edge is the only exposed area. So water ingress into this coating at the cut edge, or maybe another defect, causes leaching of these active pigments to that edge. They migrate back to the cut edge and inhibit the galvanic corrosion and extend, therefore, the service life. So on that observation, we said that cut-edge corrosion of coil-coated steel is driven by the galvanic cell. And so our hypothesis is, because it's a self-driven galvanic cell, if we use a physical model of the cut edge by putting small bits of zinc or zinc alloy separated electrically from the steel at roughly the same aspect ratio for exposed area, we can rapidly screen potential inhibitors for coil coat products. And indeed, that's what happened. So rapid cut-edge inhibitor evaluation. Here is the current flowing in that system. Lots and lots of different inhibitors. I'm not saying these are good or bad. I'm just saying these are the ones we happen to have in the cupboard at the time. Some are not very good. Some are extremely good. Chromate is off the top of the scale. But you can see we can, by analysis of the galvanic current decay over time and the final current, we can create a diagram of inhibitor efficiency versus a pigment concentration in solution. Some of these are really quite efficient. So strontium chromate has a saturated solubility of about 800, 700, 800 ppm. It's very efficient. K white has a saturated solubility of around about 110 parts per million, but also seems in this particular situation to be active, quite effective. So we can check some of these are quite good. So there's no point using Novanox because it's no good. there is a point in trying out K-white in a formulated product. This does not tell you whether the formulation works or not, it just tells you which other ones you might best to go for. Moving on a little bit further, coatings, of course, have to stick to the surface in order to survive. If they don't stick, they fail and corrosion occurs. So our hypothesis, due to Funke, was that coatings with the best adhesion also have the best performance against corrosion damage. So we did this work where we took a number of different treatments of steel, degreasing, etch priming, grit blasting, phosphating, a reactive electropolymer, and a reactive alkyd silane. These are materials where we have functional groups added which are designed to chemically link in to the backbone of the polymer. So the reactive alkyd silane had by far the best wet adhesion after 7 days, and the phosphate had the worst wet adhesion after 7 days. And yet the phosphate gave by far the best performance, and the silane treatment by far the worst performance. And in fact, the paint has been almost completely delaminated in here. It's just holding on to the skin of its teeth, as we say. So after 250 hours in a wet dry salt spray test, we can easily rebut the adhesionist performance hypothesis. Funke, in that case, was wrong. So if coating adhesion doesn't control performance, then what does control particularly cathodic disbondment performance? So we need to be worried about the generation of high local pH due to oxygen reduction, and also the generation of peroxide radicals, which are part of the mechanism for the multi-step reduction of oxygen. Then perhaps if we create a coating substrate chemistry that's relatively resistant to these activities, then we will get something that works a bit better. And we did. We used amine cured epoxy, and 3-GPS is 3-glycidyl propyl silane. That's an epoxidized silane. This is the cathodic disbonding rate for an untreated surface under the same conditions. This is the cathodic disbonding rate for the treated surface. So if we create, excuse me, if we create a surface, a chemistry that's resistant relatively to alkaline hydrolysis, then we can control or reduce the cathodic disbonding at coating defects. So that hypothesis is therefore supported. A properly chemically treated surface will indeed reduce the cathodic disbonding rate. And this is another one which was always in the literature. Water absorption into polymers is easily measurable and accounts for the observed changes in electrical resistance of coatings. And this was discovered way back by Main and others in the 1960s. And this is one of the ways we can look at water absorption is by infrared absorbance. This is the IR absorbance band. This is quantitative to water uptake, the area under that curve. So we can determine the amount of water present in the coating by reference back to a standard. So the hypothesis we have, water migrates, but ions do not migrate in polymer binders. And lots of people have said this. Sodium chloride does not attack the steel due to its low ionic permeability. And the permeability of anions such as chloride are extremely low. Lots of people have said that. I have to say, thinking about it, if those things are true, then things like desalination, polymer desalination membranes can't possibly work. But hey, we'll do the experiment and find out. So we use the infrared monitoring of hydroxyl bands and phosphate bands into paint from half molar sodium hydrogen phosphate at 40 degrees C in an ATR attenuated total reflection geometry. And we can see the water band is very steady, not a lovely Fickian diffusion. And the phosphate band is much more noisy because there's much less of a signal there to take, but we can see very clearly that the phosphate diffuses in at the same rate as the water. So they increase at the same rate, so hypothesis is rebutted. Ions, or in this particular case phosphate, do migrate in epoxy binders. So going from looking at how water and other species migrate, it's always been assumed that there is some degree of heterogeneity in epoxy and network cross-linked polymers. But if you go to from the corrosion perspective, the corrosion protection perspective, but if you go to the perspective of the polymer scientists, they have always assumed that cross-linked polymers such as epoxy behave mechanically like glassy solids, and therefore they are almost certainly physically homogeneous and probably chemically homogeneous as well. So we were very lucky to get this atomic force microscope, which had a laser attached to it, which allowed us to do infrared analysis. So although the laser illumination was diffraction limited on the surface to several microns, the sensing area is dependent on the tip of the AFM, which is nanometers in scale. So we can do nanometer local analysis of AFM, of our infrared spectroscopy. So this is the AFM image in topography mode of a resin, which is cured at 150 degrees. It's an epoxy phenolic resin. And we can see it's very flat, 30 nanometers maximum variation in topography. This here is the infrared absorption at the secondary hydroxyl cure of 116 for epoxy. And we can see this is heterogeneity of the order of microns. Okay, so the resolution of this image is around about 50 nanometers, and we can see very clearly these are micron resolution, and this appear to be associated with some of these nodules on the surface. If you look at this one here, this is the epoxy, also part of the epoxy phenolic cure reaction. Again, we're seeing chemical heterogeneity at a micron size scale. And if we look at this here, just in case this was some kind of topographic artifact, this is the polymer chain backbone. This is the methylene wiggle in the polymer chain backbone, or one of those methylene wiggles, and we can see it's uniform. So if we look at the polymer backbone, it's uniform. If you look at the individual chemical functionality, it's different. And that was the first indication that these polymers were in fact chemically different at a heterogeneous scale. So following on from that, should we expect water uptake to be chemically heterogeneous as well? And that is in fact correct. We can see these nodules coincide with increased methylene groups, so higher polymer activity, and we're also associated with increased water uptake. So epoxy network polymers are heterogeneous at the nanoscale and water and at the micron scale, and uptake into polymers is also heterogeneous at similar scale. So we rebut the hypothesis that cross-linked polymers are homogeneous. They are in fact heterogeneous. So because a homogeneous polymer does not a paint make, paint makes containing pigments. So we observe that in many cases, cavities are left in coatings after exposure to the environment. And we could postulate that these cavities form a pathway for solution ingress and for leaching of active species out of the coating. And if that's true, we can then start designing coatings from more of a mechanistic perspective than from a formulation best guess perspective. And we did this work using a time-lapse video. Should run now, there it goes. This is a nano X-ray CT of leaching behavior from a particular kind of primer. We're color coding the contents of the primer now. The blue is the leachable component, and the yellow, the yellow are the pores which are formed after a day of exposure. You can see the diffusion front just about penetrated through there. That's the back of the coating, and that's the front of the coating. And we can see these beginning to form connected pathways throughout the coating, sparse connected pathways, but connected nonetheless. And now they've penetrated after 7 days right the way through to the substrate, which is here. Some of these materials parts, some of this functional material is not leaching or not leaching within the resolution of the instrument, but some is. And clearly this is part of the mechanism. So soluble particles dissolve and leach, permitting environmental access further into the coating. And so we think that hypothesis is indeed supported in this particular case. So my final example is surface tolerant coatings. Coatings always work best if oxides and other debris are removed first. So if you try and paint this, you know it's not going to work. You need to get rid of all that rubbish that's on the surface. So the hypothesis, on the other hand, is if we can somehow penetrate into that rusty, horrible mess there and bind it all together, then perhaps it can be stabilized from further deterioration. And this is just an example of how you do the nano XRCT. There's the sample there, there's the X-ray source, and there's the detector over there. And from this, we can get a resolution, a volumetric resolution of just under a cubic micron. So here we go, painting rusty steel. So do protective coatings paint, do they really penetrate rust? I'm going to run this movie because it's fairly self-explanatory. Okay, well, obviously my student Nick, who did that, has a career wasted in corrosion. He should be some kind of movie maker. Anyway, thank you all very much. That's the end of my talk. I really appreciate you listening to it, and I appreciate again the um, committee of the EFC for awarding me this prize. Have a great conference.
Thank you very much, Professor Lyon. Dear Stuart, it was a very inspiring and a great overview of clearly many years of research. So ranging from indeed hints to a successful scientific approach towards the real and scientific depth of your tomography